Good afternoon. Welcome to Krishna's classroom. We look at yet another application of the fixed point theorem. This time from a different context. In fact, it has been possible to prove the well-known implicit function theorem using the fixed point theorem. We'll just look at the problem first of all. What exactly is the implicit function theorem concerned about? Let us take the following function f x square plus y square Now we want to analyze the whole thing using geometry and get a feel of the problem, and that would make the conditions that we impose in the statement of the theorem more transparent. Okay. So what is this? See, you have now you see that x square plus y square is greater than or equal to 0 for every xy up. Now consider the curve by a square for a belongs some a belonging to R. Then you see that the geometric manifestation of this in R2 is the following. It's a circle of radius A with the center at the origin. And of course it passes through on the x-axis it intersects at A0 and minus A0, and on the y-axis, this x-axis is the y-axis, on the y-axis it intersects at the point 0 A and 0 minus A. And there are other points distributed on the circle. So this is the situation with it. Now the question is the following. Suppose you take a point x0. Now you see that this as such is not expressed as a function, because if you solve it, what you get would be y square equal to x square. Therefore, y takes two values for each x. In fact, it determines two functions. Okay, one y equal to root of s square plus s square minus x square. The other one y equal to minus square root of s square minus x square. As such, it is not a function of x, because if you take any x that lies between, for any x a, there are two values of y in terms of x given by y equal to square root of a square minus x square and y equal to minus square root of a square minus x square. So as such, it does not define a function, because for each x there are more than one value, and therefore it's not a function. Now, how can you make it a function? By restricting the range. Okay. However, by restricting the range, one can, that is values of y, one can express y as a that is set greater than 0. Then it solves as y equal to plus square root of. So also, if y is less than 0, then it solves as y equal to minus square root of x square. Okay. So under restrictions, it defines a function y as a function of x. So under restrictions, it defines a defines y now let us take, so let x naught y naught be a point such that a square. Okay. So it may be any point on this curve C. So x naught y naught is any point on this curve. So x naught y naught belongs to C. Any point on the curve C. That is the circle C. Okay. Now the question that you ask is this. Does there exist an interval x naught minus a neighborhood of x naught where x square plus y square a square solves y giving function of x. Now let us look at this problem in a more simple scenario, that is, if the function fxy is a linear function, then what happens? Okay. Look at the situation. Where f of xy is a linear expression of x. So let dy plus c. Now let us look at the different scenario and try to solve this problem. Just analytically solve it. Suppose equal to 0. Thus, y is y then this is the question that you are asking. Is y then represented as a function of x? Or you say that if it does, then you say that y is represented as a implicitly as a function of x. This is the implicit function. The answer to this question is the implicit. Here you see that you have ax plus by equal to 0. Then you see that if b is not equal to 0, a and b are constants. Suppose b is not equal to 0, then you see that y can be represented as one upon b. And then implicitly by the equation f of xy equal to 0, suppose b is equal to 0, then zero is ax plus c equal to 0, and you see that y is represented by, so then there does not exist a function y equal to gx such that ax plus b c equal to c, because b is given to be 0. Okay, or in other words, corresponding to any x, I mean there is only one x that comes there. There are infinitely many values of y which corresponds to that. Let's look at the geometry, then it will be clear. Okay. After that, I will come back to the circle. Okay. So suppose, we split this into two cases. Suppose b is not equal to 0. Then this you see is some line like this. This is the graph of this. This is ax plus equal to 0. And you see that it is inclined to the x-axis. It may be that or maybe this, depending on the values of this. Okay. These are all possible cases. These are all possible cases. These are all various representations. B is not equal to 0. It's represented by a straight line inclined to the x-axis. So minus a by okay, a can take any value irrespective of what value a takes. Depending on what value a takes, it will be a line. However, and you see that in that case, take any point x naught y naught on this. Now you see that on the entire line R, this is the point x naught. You have the entire line R as a neighborhood of x naught, on which this solves as a function for y. Then on infinity, neighborhood of x naught, we have y equal to 1 by b now this is the function gx, so that f of zero infinity, or we say that fxy equal to 0 is represented by y equal to gx in the sense that Infinite. So that is the solution, representing which is equivalent to this. And that happens on the whole of minus infinity plus infinity. Okay. However, there's a problem. Because 1 by b is not a real number. Okay, it is either plus infinity or minus infinity. Defined on any interval such that f of 0. What is the difference? The difference is that b is equal to 0. To examine the geometry, this is what it is. See, this is ax plus b equal to 0. So we have, in fact, passes through some point. So let then there does not exist any neighborhood x naught in which and y equal to gx which satisfies the equation. Now what is happening? You see that corresponding to, you take any neighborhood of x. take any neighborhood of x0. So this is x0, 0. Take any neighborhood of x. Now you see that there is no corresponding to x0, there does not exist a y such that f of xy equal to 0, except at x0, where for any value of y, in fact it determines infinitely many values of y. So there are, when x0 is not equal to 0, there does not exist y such that f of x equal to 0. Sorry, when x is not equal to x0, but when x is equal to x0, the map x0 map to y belonging to R for any y solves the equation rather trivially, but it is no more a function. The reason is this, the graph of the function, the reason is now a vertical line whose slope is infinity. That's a problem. And this corresponds to suppose okay, because what is the slope? The slope is that y equal to minus a by. This is the slope, okay, and which is not a real number. See, when both A and B are equal to 0, then it simply means you are looking at C equal to 0 also. So that's a sort of pathological case. So b equal to 0 is something which is going to give you trouble. Therefore, we infer that b equal to 0, something that gives trouble. Therefore, we infer that ax plus by plus c equal to 0 represents a function y equal to gx if and only if, let us say, use the word implicitly, if and only if b is not equal to 0. So how do we get b from this? Okay, observe that dy. And and the function fxy equal to 0, that is b not equal to 0. So let us keep that in. Now let us come back to our circle. Problem in the that is the situation of a circle. When does a circle represents when and where? Okay. Is represented y equal to gx, x belonging to some interval delta to some interval, so that x naught plus delta this is the question that you have. Okay. Let us first once again return to our circle. This is the circle. Now suppose x naught y naught is a point here. Suppose x naught y naught is such and x naught is not equal to plus or minus 2. That means we are excluding these two terms. So we are excluding these 2 points. This is the point. Now what happens? Now you take this point, this is x naught. You can choose a neighborhood of x naught. Here, this is x naught minus delta to x naught plus delta, such that on this interval, the graph of the function that is determined by this, see, so this gives a if you take an x here, x gets mapped to this is gx. So this is from x to x. This is how the mapping takes place. So you see that for each x there is a unique point on the y-axis determined whenever you are in this kind of interval. That is the interval I have marked here. We will make it explicit. Okay. But universally this does not happen. So if you take an interval which is say the whole of R, it doesn't happen. And you see that unless you restrict the range, as I said in the beginning. So if you don't restrict the range, then this doesn't happen at all on any interval, because what happens is you have 2 different values, y naught and minus y naught, helping or serving the purpose. So gx naught will be either plus y naught or minus y naught. So that's a problem. Okay. But if you restrict the domain, if you just restrict the range now, that means you choose some neighborhood of x naught, y naught. So I will put it this way. Let me redraw that. Yeah? It's better to understand these things through geometry, then it will be clear. Then we go on to analyze it further and analytically try to prove it. So we take the circle. Center, is the center. Yes. So this is the point 0, 0. This is R. And this is A 0 and this is minus A 0 and this is A square. That is the curve C. Now you see that you take any point x naught, y naught. Suppose this is the point x naught, anywhere other than these 2 points, and you choose a neighborhood of that. So let this be a sort of neighborhood of R. Now you see that once you fix this neighborhood of x naught, y naught, then there is some interval surrounding the point x naught, say this interval, where gx is given by this arc of the circle. It means you take an x here, gets mapped uniquely. Now what I want to assert is that if x naught is not equal to A, but anything such that x naught, y naught is on C, then there is a neighborhood of x naught, y naught in which the given curve represents a function of x implicitly. So this is y equal to okay. Now to complete the story, we have to look at the scenario where it is A equal to. Suppose or equally well x naught equal to minus A. That means these 2 points. Then y equal to 0. Now you take a neighborhood of this. Any neighborhood of this. Okay. Choose any neighborhood of this x naught, y naught, and choose a neighborhood of A. Then in any neighborhood of A, you will see that the arc does not define a function. Why? Because for each x here, there are 2 values determined on the circle. So we shall just note it. At A0 or minus A0 in any neighborhood, the arc of the circle, the arc is not a function of because either there does not exist a y value or y belonging to C, there exists two y, namely x square square. So you are now looking at the neighborhood of A0 or minus A0. Then you see that you are in this situation. For some portion in the neighborhood of this, except at the point a equal to x equal to a, where the y value is determined as 0. But there is no neighborhood of a where for each x there is a unique value of y determined. Now you see the distinction between the point x0 over here and the point a0. Okay. Here you see that any neighborhood you take, see the arc would represent a function. Okay. This arc would represent a function. Where of course, what I want to say is there is a neighborhood of x0 where you can find the neighborhood of x0 y0 and the arc trapped in this region with this x square plus y square equal to a square is represented by a function y is equal to x. Now if you are here, then you can find a neighborhood. Sometimes this neighborhood may have to be very small. For instance, if you are here, then certainly the neighborhood will have to be something which does not include the point a0 or minus a0. Okay, so that's the only constraint. Observe that. Why not we consider this is the problem. So what do we do? Let us closely look at this problem. Now you see that if x dot y naught is not is such that x naught is not equal to minus a or minus a, the tangent to the circle at those points is not 1. The tangent this is what you mean by, this is what I mean by take the tangent take any point x naught y naught, get the tangent all these places, or you take this point except at these points. At the tangents are orthogonal to infinite slope. Now we see that we remember the analysis on the straight line ax plus by equal plus c equal to 0. There we found that it solves to y as a function of x uniquely whenever the slope is not equal to infinity, plus infinity or minus infinity. Whereas if it is plus infinity or minus infinity, then you are having trouble. Okay? Or if it is infinity, then it doesn't solve into a function. So the hidden secret or geometric secret that is hidden here is this. Such points are determined on the curve by determining the slope of the tangent to the curve. Okay. Shows that the difficulty, the points which create problem are those where the tangent are vertical lines. vertical lines. At all other points where it is not vertical, it gives, there is some neighborhood, etc. So we'll make that statement very precise later. Therefore, we have to avoid this point. Now, for instance, on this, the tangent to the circle is vertical at A0 and minus A. So if is such that or minus A, there always exists a neighborhood of x0 where now the difference is that if we were looking at the linear case, so that if it either solves on the entire R y as a function of x, or it doesn't solve at all. Okay. Whereas here you see that the tangent to the line that we are talking about is given by itself. So it is fixed at every point. The slope of the tangent is the same in the linear case. Whereas here, the slope of the tangent is different at different places. So we have to remove or watch for the points where the tangent has slope infinity. Okay, and that is the one that we have to look for, and what that is in fact equivalent to the points where the partial derivative of y is not equal. So now you know the reason for it. The reason is this. Okay. Suppose f is a smooth. So you see, you can write f of xy can be represented equal to f of x0 y0, it's a Taylor expansion, df by dx at x0 y0 times x minus x0 plus some remainder rxy, which is the error term, or I will write error where exy when we approximate f of xy by a linear function. This is Taylor's experiment. Okay, so approximately, so the tangent, suppose then we have f of xy is approximately equal to which is of the form ax plus by plus c. Okay. Now you see that b equal to 0 corresponds to zero. So we expect the problem to solve in some neighborhood of gx for some x implicitly if df by dy not equal to 0. Okay, so you see if it solves for the tangent there, then it happens universally. But now when it comes to a nonlinear function, the problem solves locally because you can approximate the function f by a linear function in a neighborhood of any point x0, y0. Okay, so in the linear case, it solves on minus infinity to plus infinity, not equal to 0. In the nonlinear situation, it solves locally it solves locally in a neighborhood of x naught y naught, where not equal to 0. So this is the difference. So here it solves universally I think I would put it universally whereas in the nonlinear case it solves locally. Now this is the scenario that you have. Okay. As we have seen that you cannot have universally, that is on the entire minus infinity plus infinity, the function solvable, because somewhere that a0 and minus a0 will come inside that. So you will have to avoid, take a neighborhood of x naught. So note that we will have to which does not include points xy such that where equal to 0. So these points will have to be, this is the observation that you shall see that this is indeed the situation. Okay. So we shall now define properly what we mean by what is the content of the implicit function theorem, and then show that under what conditions you have the implicit function theorem valid. That's our task. I think that's a nice place to stop, and we'll continue with it later. So now you may also look into this one, my lectures, Krishna's classroom. Analysis on Rn, Rn, (25 to 7). These sections. We'll get a very elaborate discussion this problem, including how the proof comes. Now I don't intend to go into the proof in such a detail in this lecture because it is more or less repetitive. Here in the general scenario, the whole thing has been analyzed very deeply and how the fixed point theorem comes into play. So in the next lecture, I will conclude this by giving a proof of the implicit function theorem, giving the statement and the solution of the implicit function theorem. Thank you very much.